Welcome to this comprehensive chemistry lesson on crystal structures. In this presentation, we will explore the four fundamental types of crystalline solids: ionic, metallic, molecular, and network covalent crystals. Each type has its own unique bonding, structure, and properties that determine how the material behaves in the real world. There are four primary types of crystalline solids. First, ionic crystals, where positive and negative ions are held together by electrostatic attraction. Second, metallic crystals, with a sea of delocalized electrons surrounding positive metal ions. Third, molecular crystals, made of discrete molecules held by weak intermolecular forces. And fourth, network covalent crystals, where every atom is connected by covalent bonds in a continuous network. Ionic crystals are composed of positively charged cations and negatively charged anions. These are held together by strong electrostatic attractions known as ionic bonds. The classic example is sodium chloride, which forms a face-centered cubic lattice. Each sodium ion is surrounded by 6 chloride ions. The strength of the ionic bond depends on the charges of the ions and the distances between them, as described by Coulomb's law. Here we can see the sodium chloride crystal structure visualized. The blue spheres represent sodium cations, and the green spheres represent chloride anions. They alternate in a perfect cubic pattern. Each ion is electrostatically attracted to all of its oppositely charged neighbors, making the entire crystal one giant structure held together by ionic bonds. Metallic crystals consist of positively charged metal cations surrounded by a sea of delocalized valence electrons. Unlike ionic or covalent bonds, metallic bonds are non-directional. This model explains why metals conduct electricity, because the delocalized electrons can move freely. It also explains why metals are malleable and ductile, because atomic layers can slide past each other without breaking specific bonds. In this visualization of the metallic crystal structure, the gold spheres represent positive metal cations arranged in a regular lattice. The small blue dots represent the delocalized electrons that are free to move throughout the entire structure. This electron sea is what gives metals their unique combination of strength, conductivity, and flexibility. Molecular crystals are composed of discrete molecules held together by relatively weak intermolecular forces. These include London dispersion forces, dipole-dipole interactions, and hydrogen bonds. Because these forces are much weaker than ionic, covalent, or metallic bonds, molecular crystals typically have low melting points, are soft, and do not conduct electricity. Ice is a classic example, where water molecules are held by hydrogen bonds. In this representation of a molecular crystal, each cluster represents a discrete water molecule. The molecules are held together by weak intermolecular forces shown as dashed lines. Inside each molecule, the atoms are connected by strong covalent bonds. This is the key feature of molecular crystals: strong bonds inside molecules, but weak forces between molecules. Network covalent crystals are a unique class of solids where every atom is connected to its neighbors by strong covalent bonds, forming an infinite three-dimensional network. There are no individual molecules. Diamond is the classic example, where each carbon atom forms 4 single covalent bonds in a tetrahedral arrangement. Silicon dioxide, or quartz, is another example. This diagram shows the diamond crystal structure. Each carbon atom, shown in copper, is covalently bonded to 4 neighboring carbon atoms in a perfect tetrahedral geometry. This network repeats in 3 dimensions, creating one of the strongest and hardest materials known to humanity. Let us compare the properties of all 4 crystal types side by side. Ionic crystals have high melting points, are brittle, and conduct electricity only when molten or dissolved. Metallic crystals have moderate to high melting points, are malleable and ductile, and are excellent conductors. Molecular crystals have low melting points, are soft, and do not conduct. Network covalent crystals have extremely high melting points, are very hard, and are non-conductive. This visual comparison summarizes the key properties of all 4 crystal types at a glance. Notice how the strength of bonding directly correlates with melting point and hardness. Ionic crystals conduct only when molten. Metals always conduct. Network and molecular crystals never conduct in any state. Let us examine ionic crystal properties in more detail. Ionic crystals have high melting points because significant thermal energy is required to overcome strong electrostatic forces. They are brittle because mechanical force can bring like charges together, causing repulsion. Interestingly, ionic crystals do not conduct electricity in the solid state because the ions are fixed in position. However, when melted or dissolved in water, the ions become mobile and conductive. Silicon dioxide, also known as quartz, is the most abundant network covalent solid on Earth. Each silicon atom bonds to 4 oxygen atoms in a tetrahedral geometry, and each oxygen bridges between 2 silicon atoms. This creates a continuous, very strong network. Quartz has a melting point of about 1,600 degrees Celsius and is extremely hard. Quiz question 1. Which type of bonding is responsible for holding the particles together in a sodium chloride crystal? Option A, covalent bonding between sodium and chlorine atoms. Option B, metallic bonding between sodium atoms. Option C, electrostatic attraction between sodium cations and chloride anions. Option D, hydrogen bonding between polarized sodium chloride molecules. Take 60 seconds to think about your answer. Quiz question 2. What is the key difference between a molecular crystal and a network covalent crystal? Option A. Molecular crystals have covalent bonds between atoms, while network crystals have ionic bonds. Option B. Molecular crystals consist of discrete molecules held by weak forces, while network crystals are continuous covalent networks. Option C. Molecular crystals conduct electricity, while network crystals are insulators. Option D. Molecular crystals have high melting points, while network crystals have low melting points. Think carefully. Quiz question 3. Why do metals conduct electricity while ionic crystals do not in the solid state? Option A. Metals have a regular lattice while ionic crystals do not. Option B. Metals have delocalized free electrons while ionic crystals have fixed ions. Option C. Ionic crystals are nonpolar while metals are polar. Option D. Metals form covalent bonds while ionic crystals form ionic bonds. Quiz question 4. Which of the following substances would have the highest melting point? Option A, dry ice. Option B, table salt. Option C, diamond. Option D, iron. Consider the bonding in each crystal type before answering. Quiz question 5. In the electron C model of metallic crystals, what holds the metal atoms together? Option A, covalent bonds between adjacent metal atoms. Option B, electrostatic attraction between metal cations and the delocalized electron cloud. Option C, ionic bonds between different metal ions. Option D, London dispersion forces between metal atoms. Problem 1. Explain why magnesium oxide has a much higher melting point than sodium chloride. Use Coulomb's law and the concept of lattice energy to support your answer. We will solve this step by step. Problem 2. Predict whether each of the following solids will conduct electricity. Solid sodium chloride, molten sodium chloride, copper metal, diamond, graphite. Explain each answer using the principles of crystal structure and bonding. Problem 3. Identify the type of crystalline solid for each substance and justify your answer. Magnesium oxide, iodine, silicon carbide, platinum, tetraphosphorus dicoxide. Consider melting points, bonding, and properties. Problem 4. Explain the trend in melting points for sodium, magnesium, aluminum, and silicon. Why does silicon have such a high melting point despite being next to aluminum in the periodic table? Use the electron C model and bonding theory. Problem 5. A white crystalline solid has a melting point of about 1,600 degrees Celsius. It does not conduct electricity as a solid or when molten. It is very hard and scratches glass. It is insoluble in water. Identify the type of crystalline solid and justify your answer. Let us review the key concepts. Crystal structures are defined by the type of bonding between particles. Ionic crystals involve electrostatic attraction between oppositely charged ions. Metallic crystals have metal cations in a sea of delocalized electrons. Molecular crystals consist of discrete molecules held by weak intermolecular forces. Network covalent crystals have continuous covalent bonds in 3 dimensions. Melting point order is generally molecular, then metallic, then ionic, then network covalent. Conductivity is highest in metals. Hardness is highest in network covalent crystals. In conclusion, crystal structures surround us everywhere. From table salt to diamond, from copper wires to silicon chips. The type of bonding within a crystal determines its physical and chemical personality. Whether it shatters or bends, conducts or insulates, melts easily or withstands extreme heat. By understanding the 4 fundamental crystal types, we gain the ability to predict material behavior from atomic-level structure. This knowledge is the foundation of materials science and solid-state